Welcome to this explainer. If you've been following the rapid advancements in foundation models lately, you've probably noticed a massive shift. We're not just asking what can these models do anymore. No, the real question is, how on earth do we actually govern them? So today, we're going to cut right through all that noise and break down the highly technical and frankly fascinating field of AI control. Let's get into it.
Now, to separate all the sci-fi doomerism from the practical, on-the-ground engineering realities, we've got to start with a high-stakes question. How do we control something smarter than us? Our source material draws a really clear line here between AI safety, which is all about preventing catastrophic or, existential harms from advanced systems, and AI ethics. Ethics focuses on the ongoing, everyday harms happening right now, like bias, environmental costs, and labor displacement. And sure, the communities studying these areas sometimes disagree on priorities, but they both start with the exact same fundamental challenge: control.
So for this, our source material is basically acting as our field guide to map out the messy boundary between human intent and machine behavior. We're going to anchor ourselves in chapters 30 and 31. These chapters outline the precise engineering mechanisms and the societal friction points that developers are wrestling with right now to make these highly capable systems actually behave the way we want them to.
Here's our roadmap for today. First, the AI alignment problem. Second, testing and self-critique. Third, the human bias problem. Fourth, the math of fairness. And finally, fifth, inside the black box.
All right, part one, the AI alignment problem.
Think of alignment kind of like dealing with a really stubborn genie. The ultimate challenge is making sure the system gives you what you actually meant, not just some literal, potentially disastrous interpretation of what you asked for. Broadly speaking, the whole field of alignment worries about how to make these highly capable systems pursue our intended goals. Today, the main practical tools are techniques like reinforcement learning from human feedback, where humans literally score and rank AI outputs to guide the model. But, as our source points out, that only works partially.
It turns out alignment actually subdivides into two distinct, really tricky challenges. First up is outer alignment, which basically asks, do we humans even know what we want? Have we correctly specified the goal in the first place? And then there's inner alignment, which asks, does the model's internal optimization actually match the training objective we gave it? Put simply, is the system's internal wiring genuinely following our instructions, or has it found some sneaky, hidden mathematical shortcut that obeys the letter of the law while completely violating the spirit of it?
Moving on to part two, testing and self-critique.
Now, this brings us to a fascinating approach called constitutional AI, which Anthropic introduced back in 2022. The crucial point here is that it massively reduces the need for human labeling by forcing the model to evaluate itself against a written set of principles. Instead of paying armies of humans to compare and rank thousands of outputs, you just give the AI a written constitution. The model is then asked to critique its own outputs against those rules, and it actually trains on its own critiques. It's an incredibly clever way to scale safety training.
But, self-critique isn't flawless. That is exactly why we have red teaming. All the major labs rely heavily on this kind of adversarial testing. They hire people to actively try and break the AI before it's ever released to the public. You bring in humans, or honestly even other AI models, to deliberately provoke the system, craft jailbreaks, and hunt for failure modes. It's essentially ethical hacking, but for language and behavior, just to ensure those guardrails actually hold up under malicious pressure.
All right, part three, the human bias problem.
Moving from the theoretical to the very real, our source points out three core ways that human bias creeps into the machine. First, bias training data. Look, the internet vastly overrepresents some demographics, languages, and viewpoints while entirely missing others. Second, biased labels. The human beings who label the data carry their own conscious and unconscious biases. And third, bias deployment. This is the scary reality that models that look perfectly accurate in a pristine, controlled lab environment can completely fail on unrepresented populations when they're actually out in the real world.
And we have to be clear, this isn't just some abstract academic concern. It's a profound societal problem affecting everyday lives right now. For example, we've seen facial recognition systems that struggle massively with darker skin tones. We've seen automated hiring screeners that actively penalize resumes just for containing women's keywords, and we see large language models defaulting to he for doctors and she for nurses. The models aren't malicious, they are simply reflecting the bias patterns they absorbed during training.
This leads us directly to part 4, the math of fairness.
Now, since we've established the human bias problem, you might assume we just program the AI to be fair, right? Well, the math tells a very different story. Machine learning actually has multiple different mathematical definitions of fairness, and they flat out conflict with one another. For instance, you have demographic parity, which might mean ensuring an algorithm selects candidates from different groups at exactly equal rates. But then you have equalized odds, which demands that error rates, like false positives, are equal across groups. If your underlying groups have different starting distributions in the data, balancing one of these metrics mathematically forces the other to become unbalanced.
This is honestly a mic drop reality in AI engineering. You literally cannot mathematically achieve all definitions of fairness simultaneously. It's impossible. You have to choose which one matters for your specific use case. Whether you prioritize group fairness or individual fairness, demographic parity or equalized odds, there is no universal fairness setting you can just toggle on. It is always a deliberate human choice with very real-world trade-offs.
And finally, part 5, inside the black box. For our final chapter, let's look at how we actually try to peer inside the neural network itself. Our source makes a really crucial distinction here. Explainability gives us a surface-level justification for regulated fields like healthcare. It offers a human-readable reason for a decision. But mechanistic interpretability? That is the deeper, incredibly difficult quest to map the actual internal concepts and circuits of the AI. Anthropic and a growing academic field are trying to actually identify features, the internal representations of concepts, and the combinations of those features that compute specific behaviors. It is nowhere near complete, but it is basically the closest thing we have to neuroscience for artificial brains.
I want to leave you with this massive open problem in active research. As we continue to build more capable systems, how exactly do we govern a mind that eventually outpaces our own? This is known as scalable oversight. Labs are building preparedness frameworks and frontier safety frameworks to try and anticipate this. But as these models become increasingly uninterpretable and new capabilities emerge, the ultimate question remains: how do we, as inherently flawed and biased supervisors, safely oversee an intelligence that we can barely look inside of? It just might be the defining engineering challenge of our time.